Okay, so some movements across the cell membrane. We've discussed 3 of the examples. What's one? Diffusion. Okay, we can call it simple diffusion. Why might that be called simple diffusion? Why is it simple? I just asked that. That's like saying that's black. Why is it black? Because it's black. Okay? Well, what makes it so simple? Think of the molecules. I know. So what's an example of small molecules that we talked about in class? A little more specific. What type of gases? Blood gases. Okay? Yeah, that is simple. Yeah, that is what makes it simple, because the molecules themselves are so simple, they are so small. So diffusing from your lungs into your bloodstream, the concentration of oxygen is high in your lungs, so it diffuses into the capillaries of your bloodstream. Okay? That's fairly simple. I think everyone would believe that. And the carbon dioxide in your blood is higher than inside your lungs, so it diffuses outside your capillaries, into your lungs, and then out to the atmosphere. Yes, simple diffusion. Blood gas is movement of high concentration to low. Energy needed? No. No energy is required. Okay? And then what about osmosis? What's true about that? Movement of what? Water. From what type of concentration? From high to low. So does that require any energy? So think of a solute, salt, sugar, whichever, a solvent like water, okay? And then you put the 2 together and you get a specific what? Like when in math you're looking for a solution, okay? So that doesn't require any energy either. Then the next type was what type of diffusion? Not simple, but facilitated. So who can we pick on in here? Weston, you'll be the facilitator today. So what might that mean? You will be the leader up here, telling everybody what to do and how to do their job. Should I hand over the mic? No? Should we just keep going? So what might be an example of movements in facilitated diffusion? How about glucose or sugars, proteins? Why might that be? Are these really complex, or are they small enough but just, we'll just use facilitated diffusion instead, kind of a leader to allow them to cross the cell membrane? Yeah, they're too big. So they need to have a little bit of help with a facilitator, kind of like our facilitator here helping everybody else out. Okay, so then we move on to the 4th and final one. And also, does it require any energy? No, it does not. Simple diffusion, osmosis, facilitated diffusion, moves from high to low, does not require any energy, but moves different substances. You're going to want to know that in the future. So then we begin finally with facilitated, or excuse me, we did this already. And I don't think we've done this because we haven't talked about active transport yet. Because this gets to be a little more complex, and we'll talk about that here in just a moment. almost done with this material. I have something I want to show you on the overhead. We'll take the majority of the rest of the time. So with those vocab terms that were assigned on Tuesday, have those done by the 18th, which would be when? Next Tuesday. Okay? So have them done by Tuesday. And then we will proceed on with Chapter 6. It's hopefully we can, I want to say, make sense of this material here in just a few moments, not only just here, but especially the next chapter, because we want to combine these two together and keep moving. Okay. So here it says it requires energy. Why would that be? The other three did not require energy. Why does this one? Yeah, it's moving against a concentration gradient. So therefore it's like moving uphill as opposed to downhill. We don't have any. But for track practices, what different types of routes do you run for track practice? Straight north out of town here? Okay. So how many times you got to do that hill? Okay. Okay, well, we do for, that's one of our cross-country workouts as well. We like to vary that to switch it up, and takes obviously a little more energy going uphill, don't it? Maybe yes, maybe no. How many of you would like to do that a multitude of times? A workout for us possibly be 10 times running up that hill. Go up the hill, jog back down. Sprint up the hill, back down. Sprint up the hill, back down. Sprint up the hill. Windshield wipers here. Sprint up the hill, back down. Kind of doing music here, isn't this kind of? Hey, oh. Hey. Okay, I'll stop now. Okay. So, with that, my point is it takes more energy to go uphill. Okay? So, with that, I'll show an example here in just a moment. Okay? So this energy then is supplied by breakdown of ATP. So where would this take place inside the cell from prior knowledge? The mitochondria do that. Okay, so an example of this active transport would be as follows. Maybe you'd rather be doing this stuff. Yeah? Yes? Okay. All right. Well, we'll see. Last year we told you, we'll see how many of you were paying attention during physical science class, because it comes full circle in general chemistry. But, okay, please bear with me. I know my drawings aren't the best. But, okay. And probably looks like a fallen tree. I get that. And maybe this branch is off that way. Maybe another one going this way. This is one of the very first things that we possibly drew this school year. It's a special type of cell that you would find inside your body. Okay. Say that again? Yeah, nerve cells. Okay. So with this, what we see happening, okay, is we've got a whole bunch of these things floating around. When I say these things, what are we referring to? Sodium ions. That's right. Okay? So we've got all this sodium on the outside of a nerve cell. Then on the inside, I suppose we should have some in here too. But we also have some of this in here as well. Better put some, what's this we're doing now? Oops, it's supposed to be a K. All right, so when we picture diffusion or facilitated diffusion, what would you guess? What would the sodium do in that case? All the sodium on the outside of this cell, what would this do according to diffusion? Is it going to move this direction or this direction? Yeah, it moves down, and it still does that. So we got some channels inside of here that lets that sodium pass through. Okay? But the energy aspect is going the other way. Okay? With these guys here. So this active transport must be significant for a reason, so that potassium must be doing what? Going against a what gradient? So this potassium must be doing what? Going against a what? Concentration gradient. Now, to that means nothing to you. But should there be a volleyball match tonight or tomorrow night, I know Coach Williamson says on hot days, you better be carrying this with you all day long. That's true. But you also need to have what besides just plain water? Electrolytes. Okay? Because loss of electrolytes affects this balance here for all you athletes. That's why when you have a deficiency in one of them, all of a sudden one of maybe you gentlemen all of a sudden hit the ground and it looks like, oh my God, they're in such pain, but they're feeling the back of their leg because they got cramps in the back of their hamstrings. So someone comes by, pulls the leg up, pushes it out, and maybe they massage their hamstring, and then finally that decides to let go until hopefully not the next time. Hopefully you can take in enough of those electrolytes to try to restore that balance. But typically it's not going to be immediate. It's going to take some time for this to take effect. That's why it's always such a good idea to stay as hydrated as you can, but also take in some of those electrolytes that you need so that not only you're properly hydrated, but you also have the proper minerals then too, because it leads to cramping, especially on the legs. Why would you think, why aren't we cramping in your arms or chest? Because you're not using them as much. All the energy is going through your legs. Okay? That's why. But when it comes to, when we're talking about cellular respiration, we're maybe behind just a little bit, but that's okay. When we take in oxygen, where do you suppose the main parts that oxygen has to go? The brain. Where else? Say that again? Well, the lungs really isn't a muscle. The heart is one, and then the diaphragm's the other, okay? Because those continually need to supply that energy to keep contracting and keep you breathing as well. But a lot has to go to your brain then as well to keep these reactions going, okay? So, for the rest of the time, this might start out a little slow, but it deals with they talk about ultra marathon runner. And what do we know? What's a marathon then? 6 miles. Trust me, the first 26 are really easy. It's that last point 2 that is so hard. I ran a marathon. I finished it. I didn't run the whole thing. Let me clarify that, if that makes sense. So this was quite a few years ago. It was actually back in 2011. I still got the shirt that says "We will never forget" because it was actually on Sunday, September 11th, 2011, 10 years after that. Okay, so with that, okay, what do you suppose the difference might be between a marathon and an ultra marathon? This is like 130 miles, I believe. Okay, that probably takes, I'm going to say, 3 or 4 days. And it's not so much the distance, but where it takes place. Just take a guess. Hot, hot, hot. You're getting closer, but it's in the continental U.S. Okay, now you're in the right state. I don't think I've heard, no, the UFOs aren't going to come pick us up in Area 51. You've heard of this before, it's just not coming. Death Valley, okay? So this actually takes place going through Death Valley, which just take a guess, temperature-wise. About 130 degrees probably during the day, and here you have some of these athletes moving through there. You probably would, but if you're properly conditioned, the human body can take quite a bit, providing you take good care of it, okay? Meaning diet, rest, limit the stress, which I get it. It's all part of growing up, okay? So we try to help point you people in the right direction to try to limit that as much as possible. But, and then there's another individual that swims I want to say it's some freshwater lakes in Australia. It just tries to illustrate what the human body is going through as far as some of these reactions we're talking about with that of cellular respiration and utilizing energy and how the body's going to respond to that. Now the first portion here is more so with the skeletal system. That's why I said it's a little slow, but hopefully it'll be a little bit interesting to you people as well. So we will start this, and then we will continue this tomorrow as well. Okay? All right.
over again. Thousands of tiny little thread strands that all get bundled together, that all become perfect muscle systems. Mike has begun the ascent, each move requiring an amazing unseen dance of muscle tension and release. Our muscles are designed only to pull, not push. Most are skeletal, muscles connected to our bones by tendons, dense connecting fibers acting like rubber bands. Stimulated muscles pull on our bones, creating movement.
be that they're lighter, but muscular tone. Okay, I think it used to be at one time that perhaps, I'm not saying it's true, but perhaps maybe many women thought, I don't want to lift too many weights because I don't want to put too much muscle on. But can you women do that? No. You can put muscle on, but it's toned. It's not going to build up like it does in men. Why not? Starts with this letter. Testosterone. Women, you do have a little bit of testosterone, but not near as much as what men do. And that's where you see the different changes start to take place as you develop. So these hormones that start to multiply or become more regular when we hit our teenage years. Not we, you people hit your teenage years. Okay? So we will continue with this. We'll start